What if we told you that everyone you know, and in fact every person on the planet, actually came from amongst the stars? And not just people either, but every animal, every plant, and every life form on Earth, all the way down to the single-celled organisms that permeate every corner of our world. Ask 10 people off the street what they think of such an idea, and you'll likely find 10 out of 10 people think that you are a little bit crazy. But more than a few members of our scientific community believe that this harebrained theory might actually be our history, and we just don't know it yet. This concept is called Panspermia, an openly posited scientific theory and a competing explanation on the origins of terrestrial life. If Panspermia theory is to be believed, then not just the organic building blocks of life, but life itself is everywhere across the universe, hopping between planets in a slow, steady march from which every world eventually receives its very first inhabitants. Panspermia is a concept that has been around for longer than most theories of astrobiology, and in fact, since long before astrobiology was even a potential topic of discussion. The idea dates back at least as far as the mid-400s BCE, when pre-Socratic Greek philosopher Anaxagoras proposed the idea of seeds as a part of the cosmos. In fact, he was the first to use the word panspermia, pan meaning everywhere, and spermia, or in his writings, spermata, meaning seeds. Anaxagoras was relatively vague in his writings on the subject, but modern-day scientists take his panspermata to be the first reference to the concept that earthly life came from a place other than Earth, and that the seeds of life aren't just constrained to one or a few places, but are everywhere across the cosmos. The concept was picked up again and again throughout history, usually by philosophers and theorists trying to explain the natural world, but it came under real consideration within the scientific community in the 19th century. At that time, several theories and hypotheses were converging on the idea that life, in its early forms, probably didn't resemble life as we observe it today. The evolutionary theories of Charles Darwin implied that if all life descended and evolved from other life, then that evolutionary chain had to have some sort of origin point. But Darwin himself had not proposed a solution to that problem, leaving the door wide open for any number of competing theories to be tested and weighed against each other. Around the same time, the Can't-Laplace hypothesis posited that the solar system's origins trace back to a nebula from which not only the Sun, but the Earth itself had formed. But a critical caveat to that theory was that Earth would have been too hot to sustain life when it first formed. So, if life hadn't existed at the start of Earth's history, when had it actually arrived? The final factor in the mix comes courtesy of one Louis Pasteur, who had run enough experiments in enough ways that he had fully disproven the theory that life could come from inert matter, or in the way Pasteur meant it, that simply shoving a bunch of oxygen and carbon and other elements together didn't cause them to combine into a living thing. For the theorists of the time, those three converging realities made it all but impossible to imagine ways that life could have arisen on Earth. But when a German physicist named Hermann Richter brought back the idea of panspermia, he got a good bit of traction. Richter contended that organic life existed elsewhere in the universe, had always existed, and had always propagated itself through time and space. Sir William Thomson, better known as Lord Kelvin, supported Richter's ideas, himself adding that stones moving through space, or that is asteroids, were the likely vessel for living cells to travel across interstellar boundaries and propagate life onto other worlds. Another German physicist, Hermann Helmholtz, pitched his own support behind panspermia. In his words, quote, "It seems to me a perfectly correct scientific procedure that when all our attempts to produce organisms from lifeless matter fail, we may inquire whether life has ever originated at all, whether it is not as old as matter itself, and whether its germs have not been transported from one world to another and developed themselves whenever they found a favorable soil." In 1908, a Nobel Prize-winning Swede named Svante Arrhenius added his own fuel to the fire that microbes, specifically bacterial spores, could be transported across the universe by solar radiation. But panspermia was all but thrown out in the early 20th century when tests on bacterial survivability in space-like conditions eventually showed that they were, well, not survivable at all, and in the wake of those findings, a Russian biochemist named Alexander Oparin presented a theory of abiogenesis, how life arises from non-living matter that could have taken place on Earth. That theory turned out to be pretty good, and it became humanity's best guess on where all living matter came from. But unlike other turn-of-the-century theories that turned out to be pseudo-scientific, panspermia got a bit of a second wind in 1974 when two scientists, Fred Hoyle and Chandra Wickramasinghe, posited that interstellar space dust might actually be organic. That is to say, it includes carbon, the fundamental building block of life as we know it. That hypothesis was eventually tested and shown to be correct, with a slew of later scientific findings indicating that, yes, there was actually a lot of organic matter in space. With that came the rebirth of panspermia as a viable idea. And while Hoyle Weil and Wickramer Singer's later contentions on the subject, specifically that new diseases and epidemic outbreaks are due to new life forms entering Earth's atmosphere, have yet to gain any real support, their work on the concept of panspermia set off a rejuvenation of the topic that's continued to the present day. In modern science, panspermia is generally taken as a theory with three main requirements in order to be accurate. First, organic molecules must originate in space, and we'll take our own departure here and note that for our purposes, organic molecules must be able to originate in space. Perhaps abiogenesis here on Earth also works, and there's more than one way to get life. The idea that panspermia would exist doesn't necessarily mean that it's where we came from. Secondly, those organic molecules would have to be able to give rise to living beings somewhere other than on Earth. And thirdly, those beings would have to be able to travel interstellar space and thus reach Earth without dying. Luckily for panspermia advocates the world over, the first of those three contentions, the idea that organic molecules can exist and be distributed across space, has already been confirmed. It's not a controversial claim at present, it's just how it is. As for the second and third contentions, that's the meat of what panspermia investigation consists of today, and there's not one, not two, but there's three major hypotheses to explain how a panspermic process might work. The first mechanism to explain how panspermia would happen is referred to as lithopanspermia. That is panspermia that's got to do with rocks. In order to understand this line of thinking, we've got to know two things. Firstly, that microbes and bacterial spores can survive some pretty crazy conditions, including surviving for multiple years or potentially even longer in the vacuum of space. Secondly, we've got to know that the inside of a rock, particularly a comet or an asteroid, can conceivably be safe enough for bacteria that they could survive the heat of traveling through an atmosphere at favorable speeds. The idea behind lithopanspermia is fairly simple. Once upon a time, there was a planet somewhere where life first originated. As for how life got there, let's just say for posterity's sake that it was a matter of abiogenesis, organic compounds clustering around hydrothermal vents, for example. But regardless of how it happened, this planet became home to living beings, and then one day an asteroid or a comet or even a larger celestial body slammed into that planet. During the impact, some chunks of that planet would have been driven downward towards its core, while some would have traveled outward before landing elsewhere on the planet or going into the atmosphere. But still other chunks would have been launched with such velocity that they actually escaped the planet's gravitational pull and went careening out into open space. Some of those rocks were far enough away from the impact that they didn't experience the kind of heat that would destroy amino acids or microorganisms, and now they've been launched, mostly intact, into space. If panspermia theory is to be believed, then those space rocks might have had stowaways on board, microbes that were previously underneath the planet's surface or living inside of rocks. And for all they know, things really started to shake and then got rather cold. If those microbes go dormant instead of dying outright, then congratulations to them, because they're now traveling on a journey through interstellar space. Shielded from ultraviolet radiation, on account of being trapped inside a rock, these microbes are known here on Earth to be able to tolerate extremely low temperatures, surviving in a dormant state for as long as potentially millions of years. Then, after however many millennia traveling through space, a small proportion of those space rocks might experience their big moment, plummeting down into a new planet's atmosphere and then slamming into its surface. Now, of course, there are a few other conditions here. That new planet has to be habitable, at least somewhat, and the falling space rock must be big enough that during the extreme heat of atmospheric re-entry, it can shield some of its inner parts from the worst of the landing. But if those conditions are satisfied, then those little microbes inside their space rock have just found a new home. Of course, we've got to acknowledge that we're talking about a journey of thousands or potentially millions of years, a set of potentially very unlikely conditions required in order to propagate life, and the idea that the process would have happened enough times that some living being would find its way to Earth. But remember, we're thinking on a cosmic scale here, not a human one. If one planet out there becomes host to life through abiogenesis, and that planet is hit by one comet, we could conceivably be looking at thousands of space rocks that escape the planet's atmosphere, carrying living beings inside, and potentially hundreds of those that have kept those beings alive during atmospheric re-entry. Say that a handful of those space rocks encounter other worlds, and that even 2 or 3 of those worlds are habitable enough that their microorganisms survive, and now, in the space of, let's say, 1 million years, we've potentially quadrupled the number of life-bearing planets in the universe. Repeat that process for each life-hosting planet every, let's say, conservatively 100 million years, and within the first billion years of the process beginning, we're now talking about hundreds of thousands of planets hosting life. The universe is 13.8-ish billion years old, and the planets are believed to have started forming within about 1 billion years of that. The Earth is barely 4.5 billion years old, so if conceivably abiogenesis took place somewhere in the Milky Way within the first few billion years of the universe's existence, then by the time Earth came around, some 6 or 7 billion years later, the entire galaxy could be inundated with life still propagating from that first life-bearing planet. It's a process that stretches the limits of human imagination, and one that takes place on timescales that we just can't understand in any real way. But it's absolutely possible, at least in theory. Now, every theory of panspermia has got to at least try and address one more problem. If life is so abundant in the universe, then why haven't we noticed it yet? Lithopanspermia proposes a few decent answers. For one thing, perhaps we've simply not looked hard enough or in enough places. For another, maybe asking a question like, where are all the rocks filled with alien life, simply shows that we humans don't comprehend the timelines and scales that we're dealing with here, and the next life-bearing rock won't fly by for another 1,000 years or so. Perhaps the problem is that the life forms we're talking about are specialized for deep space travel, meaning that their biosignatures are more subtle or outright different from what we'd expect. Or maybe the space rocks that got life to Earth didn't come from deep space at all. Finally, there's a fairly decent chance that they came to Earth from Mars, a much shorter and more plausible distance away when our next-door neighbor was more Earth-like and potentially teeming with life. As we move away from Lithopanspermia, we're going to circle back to a name that we already mentioned before. One Svante Arrhenius, that Swedish Nobel Prize winner we mentioned a little while ago, posited in 1903 that panspermia could exist. But Arrhenius' postulate was a little bit different than anything that we've heard about so far. The key distinction is that according to Arrhenius' logic, microorganisms didn't actually have to start their lives on a planet at all, and they didn't have to be encased inside a rock in order to make it to another world. Instead, since the raw organic materials required to create life existed in outer space, a theory that's since been strongly supported, microorganisms could potentially be generated from deep space, carried aboard tiny grains of dust, or even pushed along by themselves. As Arrhenius argued, a particle that's at or smaller than the size of 1.5 microns would be propelled across the cosmos at high speeds due to the radiation pressure of stars like our sun, basically riding a wave of light as they're spread throughout the universe. The principle is called Radiopanspermia, and before we get into the problems with this theory, we've got to emphasize some of its positives. First, if we accept the premise that the building blocks of life can somehow come together in deep space, then we immediately cut out the need for long periods of interstellar travel. Life could conceivably form right above the atmosphere of a planet and simply float down or be propelled through space for shorter intervals of time. We already know that some forms of life, like the tardigrade, can survive prolonged exposure to the vacuum of space as well as cosmic radiation, and while they can't survive forever, it stands to reason that if a living being arose in space within just a few days' journey of a planet, it could finish the trip before dying out. Additionally, the radiopanspermia concept sends the potential incidence rate of life in space through the roof. If microbial life can arise in space, and the building blocks to life are everywhere, then a whole lot of life should be popping up all across the universe. If even a small fraction survives long enough to get to the atmosphere of a habitable planet, then over the course of millions or billions of years, then the average planet is probably getting showered in living organisms. But as interesting as radiopanspermia is, it's also a theory with some serious holes. Starting, of course, with the fact that there's a whole lot of radiation in space, and no known earthly life forms could stand up to it for more than a few days, with the vast majority dying before that. The vacuum of space also takes its own toll on DNA and RNA, suggesting that unprotected DNA or RNA isn't particularly likely if it's meant to simply be powered by the pressure of light. These figures change if we're looking at microorganisms that are shielded by some sort of encasing material, or that life in a solar system where a red giant's less lethal radiation is the only thing they've got to worry about. But if we add more material, then a limit of 1.5 microns is probably exceeded, and if we're sending a life form from one solar system to another, then any organism not going from red giant to red giant would likely die, including any that can come to our own solar system. Yet even amidst such skepticism, there's reason to believe that radiopanspermia still has some legs to it. Even if we assume most spontaneously generated microorganisms die while they're in space, the sheer volume of life forms generated suggests that at least a few would find their way to habitable places in the universe. Not only that, but humanity's current estimate about the survivability of radiopanspermic life are based in our understanding of life forms we can study, specifically ones that really like being on Earth and really don't like being in deep space. Hypothetically speaking, all it would take would be one living, replicating microorganism somewhere in the 13.8 billion year history of the universe that isn't bothered by cosmic radiation for that life form to then propagate and travel at nearly the speed of light across the stars. If that's the case, then another question emerges. Why isn't Earth constantly bombarded with tiny microorganisms from outer space? But again, we aren't likely to find such a life form if we don't know what to look for or we don't perceive it to be living at all. Now, the two theories of panspermia we've discussed so far are the ones that dominate talk around the theory today. But there is a third possibility to consider, one that takes panspermia from the result of what is basically a series of accidents and adds a little bit of intent. The idea was first postulated by one of the scientists responsible for pioneering the study of DNA, Francis Crick, and a chemist named Leslie Orgel. They were the ones who coined the term directed panspermia all the way back in 1971, when they presented their theory to a conference organized by Carl Sagan. As they explained it, panspermia didn't have to be a game of chance or microbial endurance at all. Instead, it could very well be a matter of sentient intention, with some civilization, somewhere, taking it upon themselves to spread the seeds of life across the stars. In terms of the evidence they presented in support of their claim, even Crick and Orgel admitted that the indicators for directed panspermia were fairly weak, specifically the universality of the genetic code used by living things and the abundance of the element molybdenum in living organisms as compared to its relative abundance in the Earth's crust. The genetic code argument comes from the reasoning that if life on Earth had multiple origin points or a single origin point with a pretty simple genetic code, then we would expect the genetic codes of earthly life to be much more widely variant than they are. The molybdenum argument takes a somewhat more forensic tone, that if a living organism were dependent on a certain element, it would stand to reason that the element was common where that being originated, and that it certainly wouldn't be rare, like molybdenum is, on Earth. By that logic, earthly life would have been constructed and propagated from somewhere rich in molybdenum, which in Crick and Orgel's time was not believed to match anywhere on Earth. Since then, we've discovered that it does exist at higher concentrations in the Earth's seas than in its crust, but even still, Crick and Orgel's work was enough to give the idea of directed panspermia some legs. As for why some alien civilization would want to pursue a policy of directed panspermia, we can't really say. Perhaps if a spacefaring species were capable of sending probes to alien worlds, including a bit of microbial life to populate that world, could just be standard practice, or even unintentional, with microbes clinging onto their spacecraft as living residue that isn't cleaned off. Perhaps the intent might be to lay the groundwork for later colonization in a few 100,000 or perhaps a few million years, or perhaps the principle of propagating life forms elsewhere might be as important to an alien species as, say, expansion of human civilization is to humans. Either way, there aren't nearly as many ways to test for directed panspermia in Earth's own past as there are to test the feasibility of other sorts of panspermia. Some scientists have suggested the genetic signature might have been implanted into the genetic codes of the first life forms, a sort of genetic watermark that would eventually mutate out of the genome with successive generations. But short of finding that watermark, or physically capturing some sort of space probe and finding it's got a vial of algae inside, directed panspermia is likely to remain a fringe theory rather than a valid way to explain how life made it to Earth. Whatever the means by which a life form makes it to Earth, confirmation of panspermia theory would be the sort of discovery that would reshape everything we thought we knew about our universe and about the history of life itself. For decades, the search for extraterrestrial life has pinned its hopes on finding one solitary signal, one Martian fossil, one shimmering Dyson sphere around a faraway star. But to realize that panspermia theory was right all along, to realize that life is not just somewhere out there, but everywhere, well, that's the kind of revelation that redefines cosmic history and finally gives humanity a place amongst the stars.